Okay, can everyone hear me? Fantastic. Okay, how's your Condor Week or HTC24 going? Outstanding. You want to hear the best talk that I'm going to give this hour? Me too. So I want to talk about some advanced debugging tools called eBPF and Linux. And sort of the background is there's some really powerful new tools in the perf suite and something called BPF, but I don't see many people using them. And they can save you hours or days. I'm curious, who here knows what eBPF is? Okay, who here uses it a lot? Okay, who's given the talk? So again, I see that there's a lot of interest, but maybe not a lot of expertise. So my real reason for this talk is, as the old saw goes, how can you tell when someone's an expert in something? They answer every question with, it depends, that's right. But my real sort of selfish goal here is, I'm not an expert. So my answer may be, I don't know a lot, but that's because my selfish goal for writing this talk is to learn a lot of this stuff. And that's happened, and it's been super helpful for me, and I've used it a lot. So I would encourage you, admins and even users, to start learning this stuff, because I think it'll save you, and it'll give you observability into your systems that you've never had before. So caveat, if I do say I don't know, that's because I don't know. Now, unfortunately, I call this like advanced tools because I thought that was kind of cool, but I realized that may scare people off. And these tools are advanced in that the ceiling is really high. The things you can do with them at the very end are amazingly powerful and maybe a little arcane, but the on-ramp to getting started is really quite easy. So maybe I shouldn't have called this advanced, maybe I should have called powerful or new or something like that, but please don't be freaked out by the word advanced. Now, I'm not going to describe how to install these stuff. Go find your local admin, or if you are a local admin, go copy and paste this stuff in. And the way I want to organize this talk is around a series of examples. So I have 4 or 5 examples. Now, recently, Christina came to me and knocked on my door and said, I've got a problem, or really one of my researchers has a problem. This researcher has a job that takes 20 minutes to run their laptop, but it's taking 20 hours to run on our super fast, super expensive high-tech cluster. That's not really making us look good. Why? And as a bonus, because sometimes as an admin, you do get lucky, it's not all often, as she said, it's running right now. So as an admin, what would you do if you're in this situation? Assuming that you didn't close your door fast enough and like make her go away is like my first response. What tools would you use? Anyone? strace, outstanding. So kind of before that, the first thing I did was, well, I had the running job. So I used Conda SSH to job to like get in on that machine in that same environment. Who here uses SSH to job, Conda SSH to job? Okay, all of your hands should be up. Except for those of you who only use the OS pool, where it doesn't work quite yet, in which case you should be using your hands to throw stuff at me. But we will get that working, I hope. So I run Conda SSH to job. I land on the machine, and kind of reflexively, the first debugging command I always run is uptime. And the numbers are in bold up here. The uptime is like 180. Who thinks that's kind of bad, or kind of good, or maybe meh? It depends. Oh, we found the experts. Outstanding, because you're right, it does depend, right? Uptime is not scaled from the number of CPUs, and it turns out that the uptime on this machine was 180 and has 256 CPUs. So what does that mean? That means that CPU isn't a problem. We're not requesting more than we have. Conda SSH to job shows you the PID of the job in question. I do a PS, you know, the thing that pops out to me when I run PS is it's in disk D state. D is for disk there, and S is for short-term sleep, which is kind of interesting. So right now, I break out the one tool, the one scientific method I know for debugging, which is binary search. That's right. So every debugging problem is really a binary. You can apply binary search. And you can think about, what do I absolutely, provably, metaphysically certitude know right now, and then what don't I know, and what do I want to know to move in that direction. So what do I know right now? I know I have one process. I know it's not using too much CPU, but it's running much slower than we think it should. So because the title of this talk is not advanced strace usage, what I did is I became root, because that's my favorite thing to do, and I run the perf trace command instead of the strace. And I pass it these two options, -p, PID to trace, that shouldn't be too exciting, and D duration to show only system calls that take at least 10 milliseconds. I hear there's a question in the middle. Not yet, because I wanted to try my new tools. My motto is, if I can't fix it, it ain't broke. So sometimes you want to play with the new tools, and that's kind of the motivation. So I ran perf trace. Now, normally in the past I would run strace, but I want to try my new hotness and see how it would do. And duration here says only show syscalls that whose duration is at least 10 milliseconds. Why 10? It's kind of arbitrary. If it's more than 10 milliseconds, depending on the system call, that could be bad. But duration here is the real-time duration. It's not the CPU time. It's the time from entry to exit. And some durations long are probably okay, like sleep, right? If a process is doing a lot of sleep, that's probably not going to cause problems. Maybe it is, but maybe we don't want to look at those. The tricky thing here is there's a lot of syscalls that are like sleep. Like nanosleep is the actual system call that we use. And there's sleep-like calls like select and epoll and things like that. So I run perf trace and I get this. It's running futex a lot. And I get pages and pages of output of this futex. Who knows what the system call futex does? Oh, does it always have to be the same people? What does futex do? It's going to the VDSO, right? So futex, the F doesn't stand for what I thought it did. But it's a quick mutex, and long story short, it's a lot like a sleep. So we want to throw out all these futex calls because they're just noise. Because they're, from the perspective of what I'm trying to debug, they're just like a sleep. So I want to get rid of them. So I can use the next argument to perf trace that I learned. That's the -e for expression. And I say not futex, or bang futex if you're from the West Coast, or shriek futex if you're from the East Coast. And this means show all system calls that are not futex. And what do I get then? Any guesses? So when I do that, I get this output. Does anything look suspicious here? Now, CHTC people, sit in your hands, because you debug this like every week. This is a pedagogical exercise. Anything that looks suspicious from someone, what's that? It's taken an awful long time. Yeah, so this is the read system call, and it's taken 800 milliseconds, which, by my computer math is about a second. And it's only returning 8K. So read is only returning a single 8K block, which is, as us HTC people say, is really, really small. So an 8K read should not be taking a second. So what would you do if you saw this? Cry, complain. Oh, I heard complain. So that's what I did. So I called my Ceph admin, who's suspiciously not in this room. And what's that? Dun, 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 dun. That's right. So I called my Ceph admin, and I said, hey, Ceph looks kind of horked here. What are you going to do about it? He said, oh, yeah, I'll go debug that. And 5 minutes later, the job started running fast. What's that? Yeah, exactly. How green was my valley? So, I think this is an example of how a trace command can quickly, and it's just like literally less than 5 minutes, really drill down into what could otherwise be kind of a difficult problem to debug. And we we ran perf trace again after the unnamed system administrator, Aaron Moat, fixed Ceph with the same command line option, and you'll see it went from 800 milliseconds to 20, which still seems like a lot to me, but it's 40 times faster, and we're back to roughly our 20-minute runtime that the user expected. And that's kind of a typical life cycle in the example of debugging this. And again, if I didn't have perf or even strace, you might spend an awful lot of time debugging this stuff, and it's really, really quick and easy. So I recommend you start learning these tools. Now, someone here is going to say, boy, that -e, bang, futex, that seems kind of like assembly language to me. Why do you have to be so fancy, Greg? Why couldn't you do just like grep-v like I've always done? And that kind of gets to maybe what I want to talk about a little bit more. Did you have a problem with grep-v futex here? It's kind of a leading question. No? Well, let's look at kind of a simplistic model of what Linux looks like. Maybe in some very arbitrary, abstract way, it looks like this. You've got the kernel, which is a whole mess of code, and then you have a barrier between the Linux kernel and whatever user space program you're running. In this case, it's perf. So if I was to run perf, perf makes system calls over the barrier into the kernel and gets results back, right? So you run perf like trace pid, blah, 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 blah. And then all the results come back and they have to jump over the big hurdle that is the kernel user space barrier. And that can be a lot of data, especially if we weren't filtering out that futex where we get pages and pages and pages of data always coming back. And sort of the first question is, well, what happens if the kernel can't keep up? And this is common if you've got a huge amount of data coming back. Does anyone know what happens? No? I mean, there's two choices, right? The kernel could either drop data, just drop it on the floor, sort of the Ethernet approach, or it could block and slow down the trace process, which would be good for the admin, but maybe deadly for the user. So, you got two choices, and sort of which one you want to do kind of depends on your use case there. It turns out that perf actually drops the events, which is something you should know about. Now, it does the thing that Marone loves, where it knows what it doesn't know. Something that Marone's always going on and on about is it's okay to lose data as long as you know that you lost data. Or kind of like in my personal allegory, it's okay to lose your mind as long as you know that you've lost your mind. So in perf trace, we see here, if I'm running it maybe on an overloaded system, or maybe I'm asking for too much information to come over that kernel barrier, you'll see these red things where it says, oh, I lost 47 events, or I lost this. So this is something to always be aware of with perf trace. But it's sort of worse than that, because it's not just that we're sending all this data over the slow kernel to user space barrier. We then run grep. And what does grep do? That's right. It goes back to the kernel to make a pipe, and the kernel gets it all the data back that it just sent to perf, the user space, and grep sends it all the way back. And we run the pipe and it sends it back again. So we've got like 4 traversals now. And of course, if you ran like multiple greps, you'd have, an arbitrary number of these kernel crossings. And that would be bad. Now, unlike perf, strace will block the calling process. And that will cause slowdowns of the callee, which can be a problem. Not just because we may care about performance, but that can also cause any program that has timing dependencies to fail. And that's really bad, because a lot of times you try to debug something, you just make it worse, and you make it harder to understand what's going on. And this is because strace uses ptrace, which is very slow and clunky interface. Now, something with performance is, I don't want you to think that I'm too obsessed with polishing screws or making everything as absolutely fast as possible, but we would like a certain level of performance with our tracing tools that we can feel comfortable leaving them on, or that we can trace some arbitrary user's job and feel pretty good that we're not going to cause it to crash or slow down or hit a deadlock or something like this. So I want to be very clear. It's not that I'm interested that perf trace is 10% faster than strace. I'm interested that I'm not going to destroy not just the performance, but maybe even the correctness of my process under trace. Yes. Oh, absolutely, absolutely. But it's much lower. You know, there's no. What's that? Oh, I hope not. uh, oh, okay. Yeah. So if the mic people, do I have a mic person? Yeah. Okay. I will try and repeat the questions. Thank you, Christina. And this is why I try and close the door before she gets in the room. Right. So the question was, does BPF guarantee that you won't have Heisenbugs? And the answer is, are you kidding? It just minimizes the chance. But again, the idea with worrying about the performance of these tools isn't that we just want to get the data faster. It's we're very concerned about the potential correctness impact on the debuggee. So let's be careful when we performance tune that. So use case number 2. Last year I had a student hourly or student intern who did some great work with the HTC24 CLI. Who here knows about the HTC24 CLI tool, a new noun verb tool? I encourage you to play with it. And he added, or as I said in my slides here, we added, but really Max did all the work. And he added a new noun to HTC24 called Condor Event Log Read. And what this does is it reads the Condor event log, as we all know. And it's very similar to the Condor user log C++ binary. Again, as we start to move functionality from the, I will say, organically grown set of tools, which have their own bespoke set of command line options and names and stuff, into something we hope is a little more consistent with the HTC24 noun verb tool, we're moving this Condor user log. Has anyone ever used these tools? Who's used Condor user log? Oh, good. So you won't have to, you don't count. I encourage you to use this new Condor event log read command. It's very handy in the same way that Condor watch queue is, in that you can get the idea of what's going on by your jobs without talking to the SCED at all. And he spent some time and he implemented the HTC24 event log tool. And this tool is written in 100% pure Python. So being, trying to pretend like I'm a good software engineer, I thought I would do a performance benchmark and compare the Python HTC24 event log read with the Condor user log C++ binary. And they're both very simple. An undergraduate could write these programs, and frequently did. They just essentially read a file that's in a given format, and they summarize the data and emit the data in a different format. They're not talking over the network. They're not doing authentication. It's just a very simple file input, output to standard out. And it writes one line per event. So if I ran Condor user log, it might look something like this. So again, I encourage you to try with the HTC24 tool. And when we did this, no surprise here, because it was in the talk, it was a huge surprise to me at the time. The C++ binary was like twice as slow as the Python program. Any guesses why? Yeah, you got me. Well, so the first thing I did is ran time, and anything look suspicious here, Lincoln? Well, if you're just reading a file and writing the standard out, if half your time is in the system, that's really kind of suspicious. And especially because when I ran the Python program, it just spent a handful of seconds in system. So as kind of a C++ partisan, that was a little embarrassing. So I used a perf trace again, but this time with the summary option. And what does summary do? Well, it's like strace-c, and that it shows a summary of all the system calls and how many were made and how many errors there were. And I got this. Todd, what pops out to you on this table? Be more specific. What do you see here? Todd says incorrectly that it's statting the user log file a lot. That's not what's going on, but we do see a lot of calls to stat there, which seems kind of suspicious, right? We're reading one file. We probably don't need to worry about it going away as we're reading through it. And we see it's actually probably fstat that's calling stat. So one really cool thing in perf trace that I don't think strace has is the ability to interrogate stack frames. So I know this is a little tiny and maybe difficult to read, but perf trace has a call graph option, and it knows how to interrogate dwarf and other debugger formats. So I did perf trace just looking at that stat file, and I got a stack trace for every time we called stat. So I control C out of one of them, and I got this. So Todd, do you want to change your answer? This took me like 5 seconds, Todd. Come on, you're really bucking for management. So Todd doesn't see anything, but I see a call in that stack trace to time local. Now, I don't know if you're like a C or Unix expert, but what do you think the time local command, the time local system, or time local library call does? It gets the current time. That's right. And you look, the next thing it says TZ set. You should know that TZ is short for time zone. So all of a sudden, we're checking the time zone a whole lot. Why are we looking at the time zone? Well, if you go up the stack or down on the screen, I suppose, you can see that we're our event reader is calling read the header. And you might know, if looking at the header, that it's got a human readable time format in there that's implicitly in some time zone. And it turns out the POSIX spec says that every time you turn, you do a time zone calculation, you have to check the etc time zone file to make sure that your lovely administrator, Moat, has not changed the time zone in the 3 nanoseconds since the last time you did this. And it turns out that every time we are reading event, even though the read was buffered and we were only opening the file once and we weren't really doing any file I/O, we would have to check to see the etc time zone file was still there and its M time, its modification time, hadn't changed at all. And that was about half the time, half the system time that the Condor user log program was running. And so just to test this, I explicitly set the time zone to an environment variable so it knows not to check the default on the system. And I knocked 7 seconds right off, or what is that, 20% off the runtime, and more importantly, like almost 50% off the system time, which we only have one kernel. And more importantly, more embarrassingly, because this this read header is in the common Condor code base, this isn't a problem only for this Condor user log tool, which fortunately no one was running because they hadn't heard about it, but because we like to share code, because sharing code is good, every Condor program that reads the log, like Dagman, was subject to the same problem. So we fixed it in the code, and we were able to get a pretty significant benefit across Dagman and everything that reads the log, just because we were able to quickly trace this one program. Yes, the comment was, this is why we don't strip the debugging symbols out of our binaries. We try and ship, or now with RPM, we can separately ship the debug symbols, and we can get access to this. So again, because we knew that this perf trace, we get access to this, and I don't think this is something that's super advanced. I suspect that in the same way that we have problems with the code that Todd writes, we might have similar problems with code that the end users write. We might want to look at them in the same way. So the interesting thing about the perf trace summary is it's getting a huge amount of data, and again, throwing it over that kernel wall, like we were talking about before, and that useful data for all the system calls, especially for a program that's running a lot of system calls, can be tremendous, and it can be actually very slow to get all that information from the kernel into the user space, especially if we just want a tiny part of it, or maybe some reduction or some subset. So what we really want to do is we want to send some reduction of this useful information over to the user space, but not sending all of it. So we don't have to do the reduction or the summarizing in user space. And the way we do this is we send code to data. So instead of bringing the data to the code, we can send code to data. And this is a common pattern. We've seen this again and again over 50 years of computing. This is kind of the way JavaScript works. We have a little JavaScript code that's in our browser that can operate on data instead of going all the way back to a web server. Or this is the way that the PostScript works, excuse me, where you have a little language that can operate on your documents. And eBPF is a small little language, little processing system that exists in the kernel of Linux, and you can send programs to the kernel to operate on data on the kernel, and then get the data upon which you operated back to user space. So the big idea is we send this small little eBPF program, whose logo is this delightful little bee, into the kernel. The kernel runs that little program against our massive set of useful information and generates a small summary or a small reduction or an average or a table or something like that. And then we can just send the summary quickly over to user space because it's relatively small. Does that make sense? I know you got questions. Now, eBPF is very, I will say, comprehensive. One might say big. One might say terrifying. One might say enormous, not just with BPF proper, but there's a very large ecosystem all around it. And as I said in the beginning, with my warning about the word advanced, I would just say, don't panic, okay? Just because there's a lot doesn't mean you need to learn all of it right away. Or maybe to be more specific, I would say, don't panic yet. If this were an actual emergency, you would be told where to go and what to do. Now, before we make progress, I'd like to go way back in time, because BPF started in 2014. BPF was inspired, though, by dtrace in Solaris. Does anyone younger than Todd, which means everyone, know, have used Solaris? Yeah, okay. Even Sonos, even better yet. And BPF is a Linux process, but it was inspired by Solaris's dtrace, which did a lot of the similar things, but dtrace was inspired by Paradigm, which came 20 years before that. And who knows where Paradigm came from, other than Todd? Steve? That's right. Paradigm is a product of the UWCS department. Bart Miller worked on this, and is still working on this to some degree. So I just want to give a shout out about sort of the sometimes very long road from research to production and commercialization. But, you know, a lot of times we don't really hear about the value of some of these NSF-funded or maybe DOE-funded projects like Paradigm and Dynanst. But I want to give a shout out to Bart and UW people who inspired this whole thing. So what I hear you cry is eBPF. Well, here is my summary. And because I'm not an expert, this is surely wrong. But it's a very small assembly language interpreter in JIT compiler in the kernel that's register to register base. And what's kind of interesting is it's not Turing complete, or I should say, it's intentionally not Turing complete. What does that mean? That means there's no backward loops or no backward jumps. There's very few non-Turing languages. It's very easy to make a Turing language, right? You can have a single instruction computer, decrement and branch, which is Turing complete. Probably every programming language you've used, probably many accidentally, are Turing complete. So it's really interesting that it's intentionally not Turing complete. Can anyone think, other than Todd, of another non-Turing complete language? Yes. SQL. Modern SQL extensions are Turing complete. Yes. What? PHP. PHP has loops. Lincoln. Doll. Interesting. That's not the one I'm looking for. Steve. Class adds. Oh my God. Give that man a 3D printed Pelican. Exactly. Class adds is also not Turing complete. Do you know why class adds is not Turing complete? I'll give you a hint. It's intentionally not Turing complete. And now Lincoln will give me the correct answer. Because of the halting problem. That's right. Does everyone, oh, now we've lost Rachel. Class adds is intentionally not Turing complete because we do not want it to get into an infinite loop. If you had a requirements expression that got an infinite loop in the negotiator would break for everyone. So we want to ensure that you can have a class add language that is expressive enough to do the things we want without being so expressive that executing an arbitrary program, an arbitrary expression would cause an infinite loop. And it turns out detecting automatically if code executes an infinite loop is what we computer scientists would say hard, or maybe NP hard, or in my case, NP annoying. But eBPF is also non-Turing complete for the same reason, because you don't want an administrator who's issuing some sort of debugging command to cause the kernel to go in an infinite loop. We intentionally, eBPF intentionally restricts the language to prohibit infinite loops by prohibiting backward jumps in general. This also gives me a really horrible idea. Although eBPF is an assembly language, you usually don't write assembly language for eBPF. You write it in some higher level language which is compiled down to eBPF, like C or Python or other things. What are you thinking, Todd? We could compile class adds to eBPF. Interesting. Sounds like a good student project. And it has compilers, and it has a few kind of interesting built-in data structures that are in the assembly language. There's hash tables and histograms built into the language. And because we care about performance, there's a JIT compiler for this in the kernel, which is actually pretty good and generates pretty good code. So even though it's sort of nominally an interpreter or a bytecode VM, like Java or now JavaScript, it's actually compiled to native x86 or ARM or whatever code, and runs almost at native speed, which gives us this confidence that we can run it on arbitrary things. And you can attach these programs to any kernel probe. So you can attach this little bit of code at any one of tens of thousands of places in the kernel. And kind of the big idea is this allows you some reprogramming of the kernel, which again is super powerful. Now, usually, right about now, people will have one of two reactions. So raise your hand if you're on the left-hand side of the slide. Oh, I love you all. Raise your hand if you're on the right-hand side. Okay, Steve's raising both hands. I saw an awful lot of people who are unsure that that's okay. Both sides. So usually people say, oh my God, you can run code in the kernel? What could possibly go wrong? It's going to be security, it's going to break stuff, there's complexity. That could happen, maybe. But also it gives you almost ultimate power of what's going on. And usually people say, I've got 8 problems that I could solve right now. So we have to be a little careful with this trade-off of power and programmability. And unfortunately, I think this concern about security is maybe why Dynance didn't take over the world. Not because of technical reasons, but because this concern of what might happen. Now, because of this concern, there's all kinds of technical mitigations to try and ensure that eBPF programs are safe. And the number of probes and things that eBPF can do in the kernel has been very limited at first, and over the last 10 years has widened and widened and been allowed to do more things as we've seen the utility and the safety grow. This prohibition of being Turing complete is one of those safety things. There's also a bytecode validator, much like Java. And of course, you have to be root or have capsysadmin. Yes? Because people are worried. Well, the question is, why can you disable it, essentially? And that's because people are paranoid. And sometimes to allow progress, we have to allow the paranoid of the world to run their machines the way they want. And those are people who would be on the left-hand side of this slide. I'm kind of on the right-hand slide because power goes to my head. Now, maybe you heard me say you can write this stuff in C and compile it and attach to a kernel probe, and you're thinking, that sounds hard. You'd kind of be right. But what do great programmers do? They steal. And the BPF tool distributions come with maybe several dozen, maybe 60 built-in tools that you can use today that are these small BPF programs that, again, I would strongly encourage all admins to start using because they're so powerful and they have so little impact on the system. You can do things that you just can't do with strace or other tools. Here's an example, and I'm going to assume that you all can read. So I'm not going to go through these one by one. But let's take exec snoop and its favorite user, moat. So again, here's another sort of use case that we had. Do we remember, I think we talked about the SCED daemon core duty cycle in Will's talk yesterday. So we know that when the daemon core duty cycle on a SCED is high, over 95 or 99%, we know that there's a problem. Until Will showed up, we didn't have a good way to figure out what exactly was going on. So one day I successfully avoided Christina, but then Moat came into my office and said, daemon core duty cycle is high on one of our APs. What do we do? I said, no. And so I ran exec snoop, and I got this output. Does anyone notice anything here? A lot of shells, yeah. Anything else? A lot of condor queues. So I then did a PS tree and said, what's running all these condor queues? Guess what it was? Someone was running this command here. You want to know what the -n.1 does? Yeah, that's right. So this runs Condor Q 10 times a second, or as we call it, it's the SCED killer. So we killed the watch program. We thought about going after a user, and the AP returned to normal, and the DC-DC dropped to a reasonable thing right away. And again, this is because we could run that exec snoop, and it showed exactly what was going on. Now, if you remember, the watch was running at 10 hertz, dash D.1. But if you look at these timestamps, Condor Q is not running 10 times a second. It's running as fast as it can, but the SCED cannot respond to Condor Qs at 10 hertz. And that's why we were at 100% utilization. So I hear you ask, the voices in my head are asking, why does this always happen? What happens if you just Google for watch Condor Q? And things got kind of bad. So the first hit was this web page at CERN that said, watch Condor Q. And it's at CERN, who's like one of our biggest users. Oh boy. And then my second hit was this notebook.community that said run watch Condor Q. And then my third hit on Google said run watch Condor Q. And I don't know if you can see the URL up there, but it's path. So, that's kind of embarrassing. Now, fortunately, I was able to fix 2 or 3 of those, and I have an open pull request in the documentation for the third. But it kind of goes to show that with code, we want to do sort of a DevOps kind of thing where we can quickly roll out changes and deploy new features that we've developed. But sometimes with documentation, that's hard because we don't necessarily have control over all the places our documentation, or maybe documentation that we haven't written, goes. So we kind of have to be careful, and this is, I think, an ongoing problem that we need to be aware of. Now, why is watch Condor Q so bad? I mean, 10 hertz? Really? Really? This is a 4 gigahertz machine with infinite memory and 100 bazilligigabyte Ethernet. Like, why? 10? Really? 10? Well, when the SCED handles a Condor Q, it forks, or actually clones. And the problem is the speed of light forking of a SCED is only 8 hertz. And again, you might say, boy, 8 hertz? Really? This is a PDP-11? No, this is a machine in 2024. It's fast. And the reason is that clone or fork is roughly linear. That's O to the N, Rachel, in the memory size of the SCED. Now, those of you who took CS536 will say, well, what happened to copy on writes? Well, it turns out that Linux does do copy on write, but just for the data pages, not for the page table proper. So it's still order n, just the constant is a little slower, a little lower. So if you have a really big process, it still takes a bit to fork it, which is sort of unfortunate. Now, who's with me going down this rabbit hole? Outstanding. Why is the SCED big? Well, it turns out this particular SCED had about 40,000 jobs in it, which is not outrageous, but it's getting there, of which almost 20,000 are held. Now, the SCED holds all of its jobs held, idle, or running in memory. And I'd just like to remind administrators that held jobs are not free. They're not expensive individually, but if you're keeping hold of tens or hundreds of thousands of them, you are going to pay for it in your fork time, your startup time, and all this other stuff. So let's be aware of our held jobs. Careful your periodic remove. But let's keep an eye on those, and let's not arbitrarily keep held jobs around forever. Something I've thought about is maybe Condor should have a default time frame where after, say, a week, or my God, we could have a knob, some configurable amount, we should automatically remove held jobs. Maybe that's something we should do. I don't know. Oh dear. It turns out that's hard. So the question is, can you use clone instead of fork and exec? And we know how to do that. We do it in some cases, but not all, because threads are hard. So, right, but we could in theory, we could spawn a thread to do this, but we're not going to do that. So back to BPF. I said BPF is powerful. One way to access it is via C or even Python or assembly language, if you're really, that kind of nerd. But there's a much easier on-ramp, and that's a program called BPF trace. And BPF trace is modeled on awk. So who here has written awk scripts? Okay. Who here likes awk? Yeah, okay, I'm in the right place. Okay. Who? Yeah. Who here thinks that awk is short for awkward? No? Okay. So BPF trace programs are much like awk, although they start with some kernel includes to find the symbols they need. But much like awk, they have a tag, kind of like an awk regular expression, that matches the probe where they should run. And then a little bit of C or awk-like code that when that probe is hit, executes with some magic globals and other stuff. And you get maps and hash tables printed automatically on exit. And this is actually pretty easy to use, even for someone as slow as me. So you might ask, well, what's a probe in this context? And it's just a place to attach code. And there's like 9 different types of probes in the kernel. I don't have time to go through all of them right now, but sort of the 3 main ones I want to outline right now are the function probe type, which is any kernel function, or the kprobe of any function. That's any function in the kernel you can attach a probe to dynamically, which is really, really cool, and it'll be called on entry, or kret probe, which is a probe on any function's return, no matter how it returns. So if the return in the middle or return in the end or falls off the end or whatever, your code will run when that happens. These are a little bit dangerous to use because the Linux kernel function names are not guaranteed to be stable across very minor versions, so you kind of know what you're doing. So there's another one, tracepoint syscall, which will attach to the syscall entry points, which are guaranteed to be stable, even if the name of their underlying implementation changes. And those are super easy to use. So with danger of having something thrown at me, I'm going to state that this is a very simple program that most administrators should be able to understand that shows BPF trace in action. So as I said, it starts with an include of some kernel header file. We probably cut and paste that from somewhere. And then we have a matching function, which is usually a probe, or it has a begin and end, just like awk. And you'll see we have some built-in functions like printf. Pretty straightforward, I hope. But the meat is the last 4 lines here. So this says on every kreturn probe of the socket received message, assign to this hash table, or to this this hash table, the sum of the return value. And the return value is the return, the EAX on x86 or ERX, RAX, which is what receive message is returning, which happens to be the number of bytes that receive returns. So by default, when the program exits, it dumps out the hash tables that you've written to. So this by itself is a useful BPF trace program. And when I run it, it says this, and when I Control-C it, I get the output here. which is super useful. So I can see what programs and what processes are reading data from the network. So that's kind of a simple example of what BPF trace can look like. And I know, like, at starting time, that can be a little tricky, but once you get the hang of this, I think you'll find it very powerful. Yes. Yeah, you don't see an explicit print for the hash table because when the program exits, any hash tables that you created are automatically dumped. Pretty cool, huh? So what's the best thing about awk? Or the best thing about beef? What is Lincoln's favorite thing about awk? Oh, come on. One-liners. One-liners, right? So in the spirit of stealing stuff, I stole a bunch of BPF trace one-liners here. I don't expect you to be able to write these, but if you can copy them, sometimes you can mutate them or just use them off the top of your head. Here's one that'll print the file and the proc ID for every open that happens on all your processes on your system. And the example output, that's tried to make sure that this was readable on the screen, so the font is a little big, but on my machine, that's a one-liner. Or if you want to get syscall counts for each process in the system, you can do that. Again, if you want to use the built-in histogram function, again, just like we have hash tables, we have histograms that are printed on exit. So this one-liner will print a histogram of syscall counts by process. Pretty cool. Or a histogram of bytes read for a given PID. Notice I'm using the /awk style matching there, which is pretty handy. And maybe I'll work in one final kind of use case that I tripped over, where I use these tools to help Igwin out. So Igwin was suffering from a network overload, but they had a hard time tracking it down to which job or what process was abusing their network. They were pretty sure it was file transfer, or maybe it was in the SCED, but they weren't sure. And their first thought was, well, Connor keeps stats in the SCED and in the history file. But we only write those when the job exits. These jobs were running very long because they were using a lot of network. And so that was kind of too late. So being a great thief, I noticed that BPF trace ships with a TCP snoop tool that did exactly what I wanted, almost. The TCP snoop trace BPF, the TCP snoop program, BPF trace program that shipped was per user, not per process. So I had to modify it a little bit. And it turned out to be a 3-slide program where I changed just a handful of lines. So the lines in red here were the lines that I changed. I had to add a receive bytes and send byte table, and I cleared that just to be productive. I have no idea what the rest of this stuff does. I copied that. So just like with awk, I attached a probe to the send and receive message, and none of this was the code as I found it. Excuse me. And I added again the lines in red. If the program name, the command is SCED or shadow, then we did the rest of the stuff, and we kept track of the user ID. And again, we built this hash table, and that was it. So when we ran it, I got this output. This is like 15 minutes of hacking, where after running it, I Control-C it, and it dumps out the hash table, which is keyed on the user ID. It didn't translate my user ID as the username. That's left as an exercise for the reader. The process it was running, the set of processes it was running, and the number of bytes that was read or written to on the wire. And we can easily see its user ID 23201 was one of our big hitters here. So that was, again, an example of how you can take an existing BPF trace program and modify it just a little bit and be good. So I thought that was cool. So going forward, yeah, Jason. Jason wants to know what the real problem was. It's sort of beyond the scope of this talk. The real problem was the user was using Condor transfer to transfer a file that was on a shared file system. So they're double dipping the network because it was pulling in and then sending it out again. End of story. So when BPF was first written, because a lot of people were in that, oh my God, you're going to kill me column, it was initially very restricted. It was very intentionally read-only. It allowed no mutation of data in the kernel. You have to be root and some other things. And as slowly, maybe over the last 10 years, as people are seeing the utility of this thing, kernel developers are getting more comfortable in giving it more power. In particular, there are now a couple of BPF probes that allow some limited mutation in the kernel. So, for example, who here uses Kubernetes intentionally? In anger, exactly. Some Kubernetes pods get access to overlay networks via a feature called Sidecar, where you have another container next to your sort of work container through which you route all your networking, so it can make decisions and it can reroute your network. There are new BPF probe locations where BPF programs can modify the per process routing tables and do that rerouting, like we did with Kingfisher. But they can do that in the kernel without having a separate container or without going in and out of the kernel space and back again like you need to do with a sidecar. A little terrifying, kind of interesting, but it sort of shows where we're going. More relevant to us, there's a new kernel probe that attaches to the device special file open commands or open system calls that let you block access to certain device special files on a per C group basis. Now, I know that was kind of a long chain here, but what it does is it lets root for all processes in a given C group block access to certain device special files. And as I'll talk about tomorrow, we now use this in Condor to block access to GPUs that are not provisioned to you. And I'm hoping this will prevent no end of headaches that we've had with GPUs over the last few years. And so the future of BPF, who knows? I think it's just going to get bigger and bigger and more powerful, and it's something that we should all learn. Now, 137 years ago, Todd wanted to write a paper called POSIX Interventions about all the stuff that POSIX didn't do that Condor needed it to do to support checkpointing and cleanup and all these things. And, you know, in the last 137 years, we've gotten some features in Linux, maybe not POSIX, but Linux that help us, like C groups and containers and things like that. But as I want to leave you with this question, should HT Condor have first-class support for BPF programs? And what would that look like? And who controls it? Is that something a SMITer can decide entirely, or maybe the SMITer can opt into, subject to what an EP admin wants? Usually you need root or maybe cat BPF or something. Is that worthwhile? I mean, think about the things we could do. You could easily trace all the file opens from your job. You could measure the performance of your job. You can trace all the DNS calls or DSN calls from a job. You can measure your network latencies. I'm sure the Pelican people could use this to do something really untoward. Should we allow this in Condor? I would appreciate your opinions on this. And what would it look like to sort of mutate or join Condor and BPF? And maybe as sort of a thought experiment, I might say it might look something like this. Terrified now. So that's my talk. A lot of this came from these two wonderful books, BPF Performance Tools and System Performance by Brendan Gregg. Most of this, the BPF Example programs are on his GitHub page. I cannot more strongly recommend that you read these books. They're fantastic. You learn more about debugging and performance monitoring and tracing than I could ever share in 100 years. And in conclusion, this isn't really a Condor talk or HTCSS talk. I hope that's okay. I think these perf tools are super powerful and very underused in our community. And if you remember just one thing, it's that BPF trace is a pretty easy on-ramp to this thing. And this is just the beginning of where this is going. So thank you. I think I have some time for questions.
Yes, we do have a couple minutes for questions.
Thanks, Greg. I think this is more than okay. This has really been great. Thank you very much. Here's a very naive question. Could this set of tools integrated with Condor ever bring back checkpointing?
Yeah, wouldn't that be great? So the question is, can we get user space checkpointing? So I think as the world exists today, because there's so little support for mutating or getting things back, we don't have that ability yet. I think as BPF grows, that's a possibility. I believe there have been some kernel list discussions of this. You know, there's an open source project, CRIU, which claims to support user space checkpointing. And like every year we check in on it, and it's, you know, I'll just say it's not integrated with Condor yet for reasons. But I like the way you're thinking.
Any other questions? In the middle?
Thanks, Greg. So for perf, you just showed, I think, just trace. Are there other interesting things hiding under perf?
Yes, there's a whole other talk just on perf. There's trace, there's you can record, you can play back, you can have access to the hardware counters, which are super useful. And again, there's like an 800-page book, which sadly is, I think, even longer from the Condor manual. I'll have to go write some Condor pages and make ours longer, that describe this in great detail. You can do perf help, and I'll show you there's a dozen subcommands. I strongly recommend you spend some time and play with it, because once you get comfortable with this, it's super useful for debugging.
Just another minute before we go to the next session. But anybody know if the next session is actually going to be in here?
I believe so.
Okay.